So counting valence electrons. So the valence shell are the electrons, valence electrons are the ones in the outermost shell only. So for example, for lithium, you would have one valence electron. Magnesium, you've got, it has the 2s filled. You have two valence electrons. The n equals 2 electrons are not really available to do anything. Chlorine, 7 valence electrons. Again, the two electrons are not, n equals 2 electrons are not available. Bromine, 7 valence electrons. The 3d electrons are not, none of the n equals 3 shell is available to interact really with the environment. Krypton, there you have, the only ones that are accessible to interact are the 8 electrons of the 2s and 4p. The n equals 3 are not available. Krypton is not very reactive, so maybe in some books you might see that it has 0 valence electrons because it's an entirely full shell. For now, we're using convention that it has 8 valence electrons available. Again, physics doesn't really care what we call things. But it is useful to have a description for what are the electrons on the outermost part of the atom that are available for interactions. Transition metals, for transition metals, we also include the d orbitals. Those are accessible for bonding as well. For cadmium, for example, the electron configuration 5s2, 5s electrons, and 10 4d electrons. So all 12 of those are valence electrons. Copper, 4s1, 3d10, there's 11 valence electrons. Now, in some books, you'll see a convention that, for copper, since it has 4s electrons, that therefore it only has 1 valence electron. The 1 valence electron, the 3d electrons are part of the n equals 3 and therefore not valence electrons. The d electrons are relatively available for interactions. So the convention that the book uses here is that there are 11 valence electrons in copper. Which one is more useful to talk about things? It really depends on the situation. So we'll be using the convention that the d electrons in a transition metal are valence electrons. However, with anything in group 1, 2, 3, through 7, the main group metals, there's no ambiguity there. For bromine, it has 7 valence electrons. Chlorine, it has 7 valence electrons. Nitrogen has 5 valence electrons. There's no ambiguity in those situations. So so that's valence electrons. And let's practice this a little bit. So let's say, what is the electron configuration of magnesium and how many valence electrons does it have? Well, so magnesium is, it has atomic number Z equals 12. There's 12 electrons. And so let's start building up and putting them all down in electron configuration. 1s2, 2s2, 2p6. How many are we up through? We're up through 10. Okay, let's keep going. 3s2. Yeah, we've built up. We're up to 12 electrons. That's the electron configuration. The condensed electron configuration is neon 3s2. There's 2 electrons that are in the outer shell, and so therefore we have 2 valence electrons. Pretty straightforward there. Let's go up to a transition metal. What's the electron configuration of vanadium? Z equals 23. How many valence electrons does it have? Well, there's 23 electrons. Let's write a condensed formula since I'm kind of sick of writing too many electron orbitals. So we'll start off with argon. Argon has 18. That's the noble gas that's the closest below to vanadium. So there's 5 more. So we're going to start with the 2 4s electrons and 3 3d electrons. That gives us 5 more electrons. And so there are therefore 5 valence electrons. So we're out to 5 valence electrons, and that is that's all there is there, and that's the electron configuration of vanadium. There's 5 valence electrons that are available for some type of reaction. Right, and that is the end of this segment. We just covered valence electrons and anomalous electron configurations for transition metals.